Hey, today we're going to be explaining organic chemistry. First, we're going to be explaining alkane, alkene, and alkyne, their similarities and their differences. Alright, so first of all, we have our alkane, and that is only single bonds within one carbon. As seen here, we have a carbon connected with hydrogens all around. Next, we have the alkene, a little different. You see that? That's a double bond. And that's connecting two carbons together with two hydrogens connected to each carbon. Finally, we have the alkyne. The alkyne is one of a kind. See what I did there? We got a triple bond here, but that allows only one hydrogen to be attached to each carbon, because a carbon, as we know, can only hold 4 bonds. Next, we're going to be explaining the general formula of the alkane. I'll take you over here. So say we have C5, and you want to find the hydrogens, H, and the formula is 2N plus 2. So we're going to be going 2N, which is 5, so we're going to go times 5, which equals to 10, and the last part of the formula is plus 2. We'll add 2 to that, and there we go. You got 12. Bring that up here, and that will be H12. So since we know that the alkene has the double bond here, we cannot add the 2 because the double bond takes up that. So instead, if it's C5 again, and we want to find for the alkene, we'll just do 5 times 2, which equals to 10. So it'll be H10 with the double bond. Finally, the alkyne. We're going to be doing Cn, which we know already is 5. And if we're going to try and find H again, it's going to be H2n minus 2, as seen here. So it'll be 2 times 5, which we, which we know is 10, right? Is 10. But since we have that triple bond, it takes up a lot of space, which means we're going to have to go 10 minus 2. Oh, I did 12. No. 2, and that equals to 8. That means the H will equal 8. As seen here. Hey Jen, why can't a methane be possible?
Because a double bond can't be attached to a single carbon. Alkenes require a carbon-carbon double bond. Okay, so 2-methylbutane would be, you start with the butane, which is 4 carbons, and then you, on the second carbon, that's why there's a 2 here, on the second carbon you find the methyl group right up here.
Alright, next we're going to be talking about benzene. Now benzene is special because it is a cyclic, which means that it's in a circle or like a complete hexagon. So a couple things to notice about benzene is that it has an unsaturated ring, which means that it has double bonds inside of it. And as you notice, there's a double bond every second bond, I guess, between all the carbons, as seen here as well. Is it polyatomic hydrocarbon? And yeah, so that's really all there is to say about benzene.
Okay, so next we're going to talk about halogenated hydrocarbons. It's when one or more hydrogens get replaced by a halogen. So a few of these would be fluoro, chloro, bromo, or iodo. And then here's an example of a tetrafluoromethane. So it's when one carbon and all 4 of them are fluoros. And then here is 1 carbon, 3 hydrogens, and 1 chloro right here. And these are all examples of halogenated hydrocarbons.
Next we're going to be talking about ozone, which is a very big topic. We'll start off by talking about photochemical smog. Now it's when UV rays pass through the troposphere layer and it attaches with the nitrogen oxides in the atmosphere. And it creates a brownish smog that is thick and it's very noticeable. But a way to protect that is the ozone layer, which is slowly getting destroyed by CFCs. Okay. So first we understand the natural ozone cycle. So when UV rays hit two oxygen molecules connected, it will detach them, and the detached molecules will find two already attached molecules, as seen here, to create O3, which is ozone. And same thing happens over here. Okay? So now that we know the natural ozone cycle, we can talk about. Okay, so now that we know how natural ozone cycle works, we can now see how the CFCs destroy the ozone layer. So first of all, we see UV rays that will hit the CFC, and it'll actually detach one of the chlorines from it, and that becomes the free chlorine. It'll come around, and it'll find an ozone molecule, and it'll actually, the free chlorine detaches one of the oxygen molecules from that, and it'll actually attach itself with the chlorine. Then after that, a free oxygen molecule from the UV ray that actually attacked one of the oxygen molecules, the two oxygen molecules, it'll come apart. So that free oxygen will actually come in collision with the ClO here. And then since the bond is stronger between the two oxygens, it'll attach, and the Cl will actually detach. So the Cl did its job by destroying the ozone, and now that free molecule will come around again and find another ozone molecule to destroy. Now, one thing to know about that is that Cls are very strong, and they will actually not die for a long time, and they are hard to get rid of. So they will continually
10,000 times.
10,000 times around. It'll actually do that. So, and that's it for that.
So next we're going to talk about alcohols. So they're in the hydroxyl group of OH, and then here's a chemical structure, the CHH, and then this is the alcohol. And then next we're going to talk about the naming. So propan, which is 3 right here, and the 2 is on the second carbon, and the ol would be the alcohol right here. So the alcohols are named by changing the ending of the parent alkane name to OL, so just drop the E. Okay, so next we're going to talk about the carboxylic acids. So here are its properties. The carboxyl group is COOH, and they would be classified in the weak acids. And then here's the structure of it, the CR, and then here's the alcohol, and then the double bonded oxygen up here. And then here's how you name it. So they always end in oic acid. So here's an example, the 2 carbons. So then this would become an ethanoic acid. And then here's your alcohol, and always the double bond up here.
All right, next we're going to be talking about esters. So the properties of esters are they are like odors and flavors, and this is the chemical structure of the ester itself. We have 2 carbon groups represented here, and connected together is a O specifically, and a double bonded O here. So naming the esters, it's a little tough, but we'll learn how to get it done. To identify the alkyl side and the carboxylic acid side of the ester, and you will replace the anyl and with il for the alcohol. So you'd put it like right here first, and then second you would have to replace the oic of the acid and replace with O8, and we'll place it second. Okay, so now it's time for the dehydration and synthesis. And how it happens is how an ester is made is it deconnects the bond here between this OH and this carbon. And for now, we'll just like remove that. And then it'll remove, oh, it still has a bond here, we're waiting for that. And then to connect it all is an O, so another H gets removed here. And then these right here bond together. So that means that we've removed H2O. So that is dehydrating the molecules. So that's why it's called dehydration synthesis. And yeah, that's all.
Okay, so now we're going to talk about how to compare functional groups. First, we're going to have aspirin and oil of wintergreen. So they're both unsaturated. They both have double bonds. The aspirin has no alcohol because of the carboxylic acid, and this one does have alcohol because there's no carboxylic acids. And then they both have benzenes, and they both have no halogenated hydrocarbons in them.